Today we're going to be discussing the Sun, Chapter 16, and Chapter 17, Giants, Dwarfs, and Main Sequence Stars. So the Sun has a mass of approximately 2.0 times 10 to the 30th kilogram. Its radius is 700,000 kilometers. That's about 100 Earth radii. The mass is about 300,000 Earth masses. The density is about 1,400 kilograms per cubic meter. Its black body curve indicates a surface temperature of 5,800 kelvins. So the Sun has zones, or it has a structure to it. It's not just a ball of fire in the sky. If we go from the centralmost portion of the Sun, the core, and that will extend out to a distance of approximately 200,000 kilometers. In the core, we're going to have a temperature of 15 million kelvins and a very high density, 150,000 kilograms per meter. And all this energy is coming from the thermonuclear reactions, fusion reactions, which actually, we'll have more to say about that later, but those reactions don't even take place until you get up to temperatures around 10 million kelvins. So we're considerably above that. The next zone as we move out, which extends from about 200,000 kilometers out to almost 500,000 kilometers, is called the radiation zone. Here the temperature is 7 million kelvins, density is 15,000 kilograms per cubic meter. Here photons are being produced, there is electromagnetic energy, but within the radiation zone, none of the photons actually escape. So this region is actually opaque to electromagnetic radiation. Even though it's being propagated in there, it doesn't get out of there. However, the energy does get transferred to the next zone, which is called the convection zone, and that extends from 496,000 kilometers out to 696,000 kilometers. So another 200,000 kilometer wide zone. Temperature here is approximately 2 million kelvins, and the density is now lower, 150 kilograms per cubic meter. Here, heat is being produced by the process of convection. That is, that there's actually a physical transfer. Rather than heat radiating out, it's actually being transferred by movement of hot gases. So hot gases are moving up to the top of the zone, and the cooler gases are moving down deeper into the zone to be reheated. So this is the convection zone. Then we go into the photosphere. That extends from 696,000 kilometers out to 696,500 kilometers. So only a 500 kilometer zone. And this particular zone, the photosphere, the part that when we actually look up at the Sun, that's what we actually are seeing, the photosphere. So here electromagnetic energy is escaping a little bit more than 8 minutes, 8 1/4, 8 1/3 minutes, something like that. Those photons that are emanating from the Sun actually reach the Earth, enabling us to see it. Surface temperature is 5,800 kelvins. The density here is 2 times 10 to the minus 4th kilograms per cubic meter. From the photosphere, we go then to the chromosphere, which extends from 696,500 down to about 698,000 kilometers. The chromosphere is somewhat cooler, lower atmosphere of the Sun. Temperature is 4,500 kelvins. Pressure 5 millionths of a kilogram per cubic meter. Next we come to the transition zone, which extends from 698,000 out to about 706,000 kilometers. And that particular zone, the temperature is now starting to go back up again, and it's around 8,000 kelvins. The density is down to 2 times 10 to the minus 10th kilograms per cubic meter. From the transition zone, we go out to what is known as the corona. The corona is something that we don't normally see, and the only time it's actually visible from the Earth is during a total solar eclipse. So when the main body of the Sun, the photosphere, is actually blocked out, it's possible to observe the corona. The corona extends from 706,000 kilometers, extends outward. Really don't know exactly where that ends, but the temperature in the corona is again quite high. It's around 3 million Kelvin. Density is 10 to the minus 12th kilograms per cubic meter. Beyond this, we're going to have the solar wind. And the solar wind is at about 10 million kilometers. And the temperature here is greater than a million kelvins. The density is only 10 to the minus 23rd kilograms per cubic meter. So that's extraordinarily low density, meaning that there's very, very little matter actually in the solar wind, but it's essentially particles that are escaping into space and flowing outward towards the Earth and through the rest of the solar system. At the top of our atmosphere, we receive about 1,400 watts per square meter, which is called the solar constant. That's the amount of power that we're getting per square meter of surface area. And at the Earth's surface, on a clear day, about 70% of this will actually reach the surface. 50 to 70%, depending on whether there are cloud covers, severe the cloud covers are, and the atmosphere will absorb perhaps another 30% of the sunlight. If there's no clouds at all, we can expect no more than about 70% of that 1,400 watts per square meter. So that would give us about 1,000 watts per square meter. And since the average person has a surface area somewhere probably around half a square meter, the surface area of their bodies, that means if you're out there in the sun, you're getting about 500 watts, like sitting next to 10 50-watt bulbs. That's the amount of heat that you're actually receiving, or the amount of power. The luminosity of the sun is the solar constant times the surface area of a sphere with the sun at the center and the Earth on the surface. So you have to imagine that the sun is here, the Earth is out here, this is the orbit of the Earth, and that actually forms a sphere. So it's a large sphere. Its radius is 1 astronomical unit. If we do this multiplication, we take the solar constant, we multiply it by that surface area. The area actually turns out to be 2.8 times 10 to the 23rd square meters, and this gives us the luminosity of the sun, which is 4 times 10 to the 26th watts. The sun is in what we call hydrostatic equilibrium. This body is the sun. Then we've got two different forces that are actually acting on it. One of them is, because of the incredible temperature of the sun, there's an outward force that if that were the only force acting on it, the sun would just explode or would just blow out into space. However, at the same time, the sun has a very, very strong gravitational force. So gravity is pushing the sun inward. And it turns out that at its current temperature, these sets of forces actually balance one another out. So this is called hydrostatic, even though it has nothing to do with water. This is referred to as hydrostatic equilibrium. As we'll see later on, when this is disturbed, and it will be probably in another maybe 5 billion years or so, when all the hydrogen in the sun is depleted, the sun will start to cool off. That means that we're not going to have so much pressure going this way, and the sun will begin to shrink. But as it shrinks, it's going to heat back up again. And then a new set of reactions will occur that will start getting helium burning. And then you'll get much greater pressure inside than on the outside, and the sun will expand considerably in size. But we'll talk about that in a later chapter. So the core is nearly transparent to radiation, as there are no electrons left in the atoms of the core to capture photons. But the radiation actually doesn't escape. But in the radiation zone, that's where photons are actually being absorbed. In the convection zone, hot solar gases move outward and cooler gases move inward. In the photosphere, electrons are getting excited to higher energy levels as they fall back to the ground state. Well, photons are being emitted, and these do escape the sun. The surface of the photosphere is mottled, and it consists of granules that are about 1,000 kilometers across. Now these granules have sort of light and dark areas to them, but the darker areas only appear dark because of the fact that they're a little bit cooler, and it's not very much. It's only 500 kelvins cooler than the surrounding lighter areas. There's also what are known as supergranulation regions, which are about 30,000 kilometers across, and these probably come from a deeper layer of the sun and are a collection of large convection cells. So if we look at the composition of the sun, and we're getting that really from the atmosphere, in terms of atoms, it's 91.2% hydrogen and 8.9% helium. And that just in terms of the number of atoms. But if we're actually looking at it in terms of mass, it's 71% hydrogen, 27.1% helium, and then there are 0.97% oxygen, 0.4% carbon, and then the remaining elements that I'm going to name, nitrogen is 0.09%, silicon about 0.1%, magnesium 0.076%, sodium 0.058%, iron is 0.14%, and sulfur only 0.04%. Those are the principal constituents of the sun. Now, from the chromosphere, when we look at this through telescopes, we can see spicules, kind of a spiky material, escaping from the chromosphere, and it's moving at 100 kilometers per second. These originate from small solar storms, and they're constantly taking place over about 1% of the sun's surface in areas where there's a strengthening of the magnetic field. In the transition zone, there's a shift from absorption to transmission. So remember that in the inner zone, none of the photons were getting out. So once you get into the transition zone, you start to get to the point where some of the photons are actually not being absorbed, but they're actually emanating from the sun. The reason for the high temperature of the corona, temperature gets up to about 3 million kelvins, and it's not entirely understood what's causing this, but it may be caused by magnetic disturbances in the photosphere. So very, very strong magnetic disturbances could cause that heating. The solar wind is evaporating the sun's mass very, very slowly. I would say a little bit less than 0.1% of the sun has actually evaporated away since the sun was formed 4.6 billion years ago. Sunspots are another feature of the sun. They were first observed by Galileo. There is a dark central area to sunspots, which is known as the umbra. Before, when we had the umbra and the penumbra, so the darker area is the umbra, and then there's a grayish outer area, which is the penumbra. The spots are about 10,000 kilometers across on average. That's the size of the Earth, and they occur in groups. The penumbra is hotter than the umbra. The umbra is about 4,500 kelvins, and the penumbra is about 5,500 kelvins. So it's still 300 kelvins cooler, which is the reason that we're able to see it at all, than the actual surface temperature of the photosphere itself. The sunspots are caused by increased magnetic field flux. It's about 1,000 times that of the rest of the photosphere. In these areas, field lines are perpendicular to the sun's surface. If you could see the magnetic field, if this is the sun, again here, and say this is the equator of the sun. In the northern hemisphere, we'll see groups of sunspots wherever the sunspots happen to be, and they'll never be more than 60 degrees north or 60 degrees south. But what we'll see is they will actually come out of the sun perpendicular to the surface, and then they'll go back in. So they'll form a loop like this. So you have these magnetic flow lines. We call it, where they emanate from the sun, at least magnetically, is the south pole of that sunspot, and then the north would be over here. And you could have another one up here, and it's the same orientation, south to north. So they're going back in on the north, coming out on the south and going back in on the north. But when you're in the other hemisphere, where the poles are opposite that, so they're still coming out from the south to the north, but now the flow is this way. So it's kind of like that. They last from about 1 day up to about 100 days. The average number reaches a maximum every approximately 11 years. That could be anywhere from 7 to about 15 years. They fall off to 0 at some point, and then they start over in a 22-year solar cycle. After 11 years, the spots reverse their polarities, and these changes are believed to be due to the differential rotation and convection currents interacting with the sun's magnetic field. There was, between the years 1645 and 1715, a period known as the Maunder minimum, where there were very, very few sunspots, and most of Europe and probably the colonies were thrust into summers that were extraordinarily cold. And there is, I think, in your book, a painting that was made during this time period that shows people dressed up in their winter clothing, and it's in the middle of the summer. In addition to the solar activity that I've already talked about, there's a series of energetic events that occur at sites that are called active regions, and these regions are associated with phenomena known as solar prominences, flares, and coronal mass ejections. So prominences are loops of glowing gas that may be tens of thousands of kilometers apart. They radiate something on the order of 10 to the 25th joules of energy. Flares are more violent than prominences, so that's another form of energy release, and these are kind of explosive releases. In a solar flare, you can get temperatures approaching 100 million kelvins. And they're short duration. They last perhaps just a few minutes. Then coronal mass ejections are giant magnetic bubbles of ionized gas that actually separate from the solar atmosphere. So you could think of the sun as being like a hot pot of soup, and a bubble forms, and then this material that's inside there escapes into interplanetary space. These occur a few times per week on an average. Coronal holes are solar windows that are deficient in matter and can be hundreds of thousands of kilometers across. They appear to be involved in the process of magnetic field reversals. But again, this process is not particularly well understood. And spicules and magnetic disturbances postulated at this point in time to actually be what actually heats the corona. Now the sun produces energy at 2 times 10 to the minus 4th watts per kilogram of solar material. Now that number sounds pretty small, may not sound like a lot, but if you actually look at this in terms of how many kilograms there are in the sun, and also if you look at this over the lifetime of the sun, it actually corresponds to an energy release of 3 times 10 to the 13th joules per kilogram over the 4.6 billion life of the sun. And since the sun will burn for another approximately 5 billion years, we can double that number. So we can say it's about 6 trillion joules per kilogram. And if you multiply that by the mass of the sun, you get a number that's on the order of 1.2 times 10 to the 44th joules. So that is just an absolutely enormous amount of energy.